So in section 6.2, we're going to consider an alternative method for finding volumes of solids of rotation. In particular, we're going to be looking at cases where trying to use the disk method or the washer method would have been either problematic or impossible for reasons we'll consider here. So to get started, if we were to consider a quadratic function, y equals negative x squared plus 6x minus 5, and we're looking at the region bound between that curve and the x-axis. Let's say we wanted to generate a solid by revolving that region around the y-axis. How might we go about doing this? Well, if we were to look at our area and keep in mind what we learned in section 6.1, we might say, well, let me draw my cross-section, and since we're doing a rotation around the y-axis, we would draw a cross-section perpendicular to the axis of rotation, in this case the y-axis. And if we looked at this, since there is a gap between the axis of rotation and the cross-section, we might say, well, this looks like a characteristic washer method that we're dealing with here. So based on this, we would say that's got to be a washer method. So we're going to go ahead and write this in right here. So washer method. Now, if we think about this washer method, let me go ahead and put that cross section back in there. You know, what might be some of the problems with this that we could potentially run into if we try to do a washer method? Well, one issue that we might quickly find is that the inner radius of this washer and the outer radius of this washer, inner radius, outer radius, are both the same curve. And if we tried to use the washer method formula, we would just end up getting 0 because the inner and outer radius are essentially the same function. So that becomes a significant problem for us in this case. So this is the big one, is that the inner and outer radius are the same curve. The other issue that we would run into here is that we would need everything to be as a function of y as opposed to a function of x. So we would need to take this function right here and solve it for x. That would require some really unpleasant manipulations, having to use the quadratic formula to solve this for x and treat y as a constant. So that's another really unfortunate side effect of trying to do a washer method here, is that expressing f of x as a function of y is, let's just call it, is ugly. It'd be a really unpleasant thing to do. So for these reasons, I think it's worth considering another way of approaching this problem. So let's, rather than drawing that cross section perpendicular to the axis of rotation, what if we shifted it? And what if we wrote it, or if we drew it parallel? So let's go ahead and try that next. So if we were to go in and pick a point on this region, let's just call it x sub k, something between x equals 1 and x equals 5 on our region, and we were to draw a cross section that was parallel to our axis of rotation. Now, to rotate this about the y-axis, let's think about what type of shape we would get. Well, there's a gap between the axis of rotation and the cross-section, so there'd definitely be some space in between there. And since it's so tall, what we're going to end up getting is, rather than a washer, we're going to get a cylindrical shell that is empty on the inside. So that's what we end up getting when we do this, is we generate a series of cylindrical shells. Now, I went ahead and I drew this ahead of time, just because drawing it live would have taken forever, and you guys don't want to sit there and watch me draw this. So this would have been the resulting solid that we get, along with that first shell drawn in there. So this is this point right here. This is our x sub k that we started with right there. All right, so we've got the solid that kind of looks like a bundt cake or the top half of the bagel. Now, what we would need to start to do in order to find the volume of this solid is to go through and identify the volume of all of these shells and then add them all together. So it's similar to how we approach the disc in the washer method. Generalize the volume of one of these items, and then we use integration to add them all up and find the total volume. So how do we calculate the volume of a hollow cylindrical shell? Probably the easiest way to do this is to think about making a slice from top to bottom and unraveling it. Now, if we were to take a cylindrical shell and unravel it, then what we'd end up with is a rectangular box. So unraveling a shell gives us a rectangular box. And we can go ahead and draw that to see that real quickly. So let's go ahead and open this up. So we'd get, think about if you had a tuna can or something like that, and you made a slice from top to bottom and removed the top of the can, the bottom of the can, you would just get a rectangular strip, essentially. And this rectangular strip does have some thickness to it. It's not just a perfectly flat plane. Now, this thickness right here, the thickness of this shell, that's the width of our cross section right there. So I'm going to fill that in red. So let's go ahead and start giving some names to each of these dimensions. So the thickness, since that's just the width of our cross section, we'll use our characteristic notation for the width of cross section here. We're just going to call this delta x sub k. That's essentially just, the width of that original cross section that we drew. All right, so we've got the thickness of our rectangular box. Now the height of this rectangular box. Think about what determined the height of that cross section. It was the point where it hit the curve, the distance from the x-axis to the curve. So we're just going to call this f of x sub k, the value of the function at that particular point. So the height is f of x sub k. And now to get the volume of this box, we need one more dimension. We need the length of this curve, of this box. Now the length of the box actually comes from the circumference of this shell. It's that distance around the top or the bottom rim of this shell. So the length we just define as the circumference of the shell. And we know from geometry that the circumference of a circle is 2 times pi times r. Now what we need to talk about next is this r, this radius. So if we go back and we look at our shell, the radius is this distance right here. It's that distance from the axis of rotation to that point x sub k, where we drew our cross-section on the x-axis. So I think it's worth writing this down because this is going to be the real defining characteristic of this shell method, is that we take these parallel cross-sections and they have a defined radius of the distance from the axis of rotation to x sub k. So the radius of the shell is the distance from the axis of rotation to x sub k, where we drew that cross section. In this case, that distance is just x sub k. It's just that's how far we would have to travel to get to that point from the y-axis. All right, so we've defined all 3 dimensions of this box, so now we can actually go through and calculate the volume of this kth shell. So if we defined this as our kth shell just unraveled, the volume, we'll call it V sub k, is going to be equal to 2 pi times the shell radius times the shell height times delta x sub k. And if we wanted to go through and find the total volume of this whole solid, we would just add up all of those shell volumes. So the total volume V would be the sum from k equals 1 to n of all of these volumes. If we've got n shells, that would have us adding them all up. And we kind of know where we're headed with this. If we were to let the number of shells approach infinity, so we would take the limit of the sum from the first shell to the nth shell of 2 pi, again where this is just the radius times the height times delta x, then we would then get our total volume. So I guess this probably should have come down right here. So if we let it approach infinity, the result for our region is going to be the definite integral. So here's the big payoff here, is that volume is equal to the integral from a to b of 2 pi times the radius times the height of the shell, and then dx.